This podcast involves temperature and its relationship with pressure. If you heat a sample of gas in a fixed volume container, the pressure is going to increase because the particles will be moving faster and they will exert more force on the walls of the container. Thus, we say pressure is directly proportional to temperature. As one goes up, the other goes up. One goes down, the other will go down. Let's look at a couple of sample problems. Here, we're given an initial and a final temperature and an initial pressure and asked to determine the final pressure. Since we're looking for a pressure, we're going to start with the pressure that was given and apply a conversion factor based upon the temperatures that we were given. Now, it's directly proportional. If the temperature is going up, the pressure is going up. So we're going to put the 400 Kelvin, the larger number, on top, and we end up with an answer of 2.71 atmospheres. And that answer makes sense because the T went up, the P has to go up. And we're using what we call a top-heavy fraction in the calculation. In this example, we're given an initial and final pressure and an initial temperature and asked for the final temperature. Notice that the pressure went down. So again, we're looking for temperatures. You start with the initial temperature. Now, since the pressure went down, we want the larger number on the bottom or the smaller on top. That will then give us the temperature of 184 Kelvin, lower than what we began with. This is consistent with the direct proportionality. The V went down, the T has to go down. This fraction we call bottom heavy. Now, these laws are named after Gay-Lussac or Guillaume Amonton, and it is that pressure is proportional to temperature, and it means that they're directly proportional. These two gentlemen worked on gas laws, and indeed Gay-Lussac used Amonton's work and published it.